So we already did this, that we figured out, right? We did the whole reversible thing, right? I told you that electrons, they always travel towards the higher potential electrode, towards the higher potential, right? From the lower potential. And it's a relative, I mean, I told you that potentials is a relative value. The higher potential is the one that you treat as the positive potential. The lower potential is the one that is your negative potential. So in reality, there's no plus or minus sign. I mean, that's not important. One is higher, what the other one is lower, right? So I mean, these values are relative values, and they're measured against the standard hydrogen electrode. And I told you that if the electrons travel towards the higher potential, the equilibrium over here shifts to the right because you have more electrons. So iron ions will start to gain electrons and they would start moving in the forward direction. The reaction would no longer be at equilibrium. It would instead be moving in the forward direction. And it's going to gain electrons. While the other one, since the electrons are being pulled or towards the higher potential, it's losing electrons. When it loses electrons, the equilibrium would try to make more electrons. And hence it will move towards the backward side and it will start to lose electrons. And the rule that we agreed on, right, when we were studying this was, the main rule is higher potential gains electrons. Whoever is the higher potential would gain electron, and whoever is the lower potential is the one that's going to lose electrons. So you don't have to think about it in terms of equilibrium. You can just directly think about this, that higher potential gains electrons, so it's going to move in the forward direction, and the lower potential is the one that loses electrons and it's going to move in the backward direction. Is this clear?
Yes.
So now the thing is that we can connect any two electrodes. I'm going to write down the definition of a standard electrode first. Like, we already know that we can measure potentials of any electrode with respect to the standard hydrogen electrode. So they're either going to be more positive or they're going to be more negative. If they like to gain electrons, the electrode would have a positive potential. If the substance over here or the reaction over here wants to lose electrons, there's going to be a lot of electrons over here and it's going to be negatively charged, or it's going to be lower potential compared to the hydrogen electrode. So the definition for this is that, and they're going to ask you for the definition. So the definition is for the standard electrode potential. And now that definition is that it is the potential difference that is measured between a standard electrode and a standard. I mean, literally, it's the potential difference between any electrode and the standard hydrogen electrode. That's basically the definition. And what is the meaning of the term standard? What does standard represent? Like, whenever we use the term standard, what does it represent?
Standard means that
whenever you have standard enthalpy change or standard hydrogen electrode or standard enthalpy change of combustion. So standard means it represents conditions, right? Right, 298 Kelvin. So that's room temperature, 25 degrees centigrade. Everything is going to be at 1 atm pressure. So, I mean, you're doing all of this at room temperature. And if it's a solution, it's going to be 1 mole per decimeter cube. So when you draw these electrodes, it's a lot better to actually tell them exactly what the conditions are. I mean, just to be on the safe side. Because if you're trying to measure the standard potential, then for example, over here in the solution, you're going to state that the concentration of Fe3 plus is going to be, and concentration is represented by square brackets. So that's going to be 1 mole per. And the concentration of it's also going to be 1 mole per decimeter cube. And if there is hydrogen gas, then it should be at 1 atm pressure. So I mean, you should, and if there's H+1 solution I mean, if the solution contains H+1 ions, then the concentration of the H+1 should also be 1 mole per decimeter cube. Is that clear? So that's one thing. And now we're going to focus more on reactions. What we're going to do is predicting redox reactions. So we know that higher potential gains electrons, lower potential loses electrons. That's the main rule. So high E naught gains, and vice versa, lower E naught. It loses electrons. So I'm going to open the data booklet, which, I mean, now no longer, you won't be given these data booklets, but if any data is required for a question, it's going to be quoted with the question. So they've actually, but just for the past papers, I think we still need the data booklet for the past papers. So here's, I mean, somewhere over here, right at the beginning, these are the potential tables, right? So I'm going to pick any random electrode. Just 1 second. So I'm gonna just pick, let's say I pick this electrode, and I'm going to copy this. So that's one of my electrodes. And let me pick another one. Let's pick the tin electrode. Now these potentials are given, and this is a standard way of writing it. Like in the forward reaction, they gain electron. In the backward direction, they lose electrons. Remember, at the moment, they're reversible. They only gain or lose relative to something. So here's my other electrode. So I've got these two electrodes. First one, I'm just going to quickly draw this this electrode, the one on the left side. What is it? It contains oxygen gas, right? So oxygen gas must be in a, it must be in a gas jar, right? And this is where the oxygen gas is being pumped in. So this has O2 gas coming in. What kind of electrode would there be for this particular equilibrium?
Platinum.
It's going to be platinum because remember, if only it's going to be the metal is going to be the electrode if a metal is involved. But in this case, there is no metal involved. The solution is going to contain what? It's going to contain water molecules. It's also going to contain these, whatever these ions are, H2 minus 1, and your OH ions, right? So all of them would have a concentration of 1 mole per dmq. And they would be in equilibrium with this oxygen gas that's coming in, and there's going to be a platinum electrode. And then this other one, the other one is so that's one electrode. Now the other one is simple. It's what would be the electrode made for this one?
Tin, SN.
So it's going to be made from tin, and there's obviously going to be the same type of beaker, and that's going to contain the tin 2+ ions. Tin 2+, right? Yeah, tin 2+. So tin 2+ over here, and this is going to be made from SN. So there's going to be an equilibrium. There's going to be a back and forth reaction, and this would have a potential of minus 0.14 volts, right? This other one will have a potential of minus 0.08 volts. So remember, the negative values, the values themselves, they don't mean anything. It's the difference between the two potentials. So I'm just going to connect the two electrodes with a wire, and there's going to be a voltmeter in the middle. And one thing is missing. What is that thing that's missing?
Salt bridge.
Okay, so there's got to be a salt bridge. So you have a salt bridge. So now first thing, in which direction would the electrons flow? Left to right, right to left?
Right to left.
Right to left. So relatively speaking, this is the higher potential, right?
Yes.
So that's basically your positive terminal, and that's your lower potential. So relatively speaking, that's your negative, and the electrons, they flow in this direction, right? So we're not going to talk about the equilibrium thing now. Just tell me who gains electrons, who loses electrons. I mean, you've got two reactions. Once you connect them together, they're no longer going to be in equilibrium. One of them is going to gain electrons. I mean, and one of them is going to lose electrons. So out of the two, who's going to gain electrons? I mean, is this going to, which one?
SN is going to gain electrons.
SN?
SN will lose electrons and
Yes.
oxygen will gain electrons.
So remember, the lower potential is the one that likes to lose electrons, and relatively speaking, the higher potential is the one that's going to gain electrons. So you've basically figured out the two reactions. If you and you can now predict the overall reaction. You've got your two half equations. All you have to do now is, the first thing is when you've got two reactions together, and you want to, and let me just put them right next to each other. So once you have two reactions, right, you can pick any two random reactions and you can predict what the output would be. The first thing that needs to be done is, I mean, you figured out who's going to gain electrons, who's going to lose electrons, if the two things are together, right? So all you have to do is, the first thing is, you make sure that the number of electrons gained and lost are equal. In this case, it's equal. If it's not equal, then one of the equations got to be multiplied by a certain number, or you can multiply both equations. We're going to do another question similar to that. And you can write the overall redox reaction. You can add up the reactants from the two reactions, and you can, on the other side, you can write the products that you're going to get from both reactions. So in the first one, the reactants are on the left side. Your reactants are O2 plus, what are your reactants? It's O2 plus H2O plus 2 electrons, right? So in the first one, your reactants are this. In the second one, the reactant is 10, because 10 is converting into 10 2 plus. So 10 is your reactant. So it's SN. And then you write down the products. The products are, what are your products? In the first one, the product is HO2 minus 1 and OH minus 1. That's what's being made. And in the second reaction, the product is tin 2 plus. So that's your product, tin 2 plus and 2 electrons. Now you need to simplify this equation like a math equation. The 2 electrons are going to get cancelled out. And the other things are not going to get simplified, but that's your overall reaction now. Ranchi, is this clear, this thing?
Yes, it is.
And I'll write this, that make sure the number of electrons, just like the balancing thing that we did earlier, you have to make the number of electrons gained and lost equal. And there's going to be another thing, and that's going to be known as the E0 cell. The E0 cell is going to be the potential difference between the two electrodes. Like you had one electrode, you had another electrode. So the potential difference would determine how fast, if you know physics, if you know electricity. So just a second. So if you know physics, potential difference, what does it tell you? It will tell you how fast the electrons would flow. It will tell you it will predict how quickly the reaction will happen. So if the potential difference between the two electrodes is very big, that means a lot of electrons would flow very, very quickly. Ranji, is this point clear?
Yes.
So E0 cell is the potential difference. So how do you calculate potential difference in physics? What's the formula for that? Like if I want to calculate the voltage on this cell, what would I do? It's going to be
V equals IR.
it is V is equal to IR, but I mean the potential is over here is given and the potential over here is given. So what is the potential difference over here? You already know you subtract them, and it's always the higher potential minus the
lower potential.
minus lower potential. So, but just to be technically, it's going to be the reduction E0 minus the oxidation E0. I mean, it's basically higher minus lower, but I mean, this thing matters. Reduction E0 minus oxidation E. So it's going to be, which one is the higher one? I think it's minus 0.08.
Yes.
And the lower one is minus 0.14. So I think, what would I get? I think 0.6?
0.06.
0.06 volts, right? So I'm going to get 0.06 volts, and that's the E0 cell. Now this value will tell me how fast or how feasible the reaction is. So first thing is, what do you get? What information do you get from the E0 cell? That's E0 cell, if it's greater than 0, that means the reaction is feasible. Or you use the word spontaneous for that. It's feasible or spontaneous. And the other thing about this is that higher E0 cell means more faster reaction. Or you can say a more feasible reaction. So you've got a faster reaction. So that's what E0 cell would represent. And sometimes, remember, it's sometimes this value, I mean, they can say that there's a, I mean, here's what the other type of reaction could be. Sometimes they would say that this reaction, I mean, they will ask you to figure out the feasibility of a reaction that is not happening. For example, they might give you an equation which is exactly the opposite of this. What I mean by that is, this one is going in the forward direction and that one is going in the backward direction. So if you make up the reaction, it's going to be exactly the opposite of this, right? The arrow would be pointing in the other direction. Ranji, do you get my point?
Yes.
So sometimes they'll give you an equation which is going to be an unfeasible reaction, because I mean, this is going to move in the forward direction. It's the higher potential. So if they're saying that it's going to go in the backward direction, then that means that is not going to happen. It's an unfeasible reaction. Is that point clear?
Yes.
So, which is why this reduction and oxidation is more important compared to higher minus lower, because if you take this as the one that's getting oxidized, then this is the oxidation potential, right? Minus 0.08. And if you consider this as the one that's gaining electrons, then this is the reduction potential. So if you do reduction minus oxidation, you're going to get a very big negative value. And any value for E naught cell, if it comes out to be less than 0, then that means it's not feasible. What that means is that you're doing exactly the opposite. If the E naught cell comes out to be less than 0, that means you did everything wrong. I mean, the way you're predicting the reaction, that's completely wrong. Is that clear?
Yes.
So anyway, so from now on, we're not going to draw diagrams. So I'm just going to do a couple of more reactions. Just remember, the higher potential is the one that's going to gain electrons, and the lower potential is the one that's going to lose electrons. So that's about it. Sorry. So we're just going to jump to equations directly now without drawing diagrams. So let's say I have this Fe. Where's Fe? MnO4 minus 1. Let's pick this equation. 1.52 volts, and the other one is, let's pick, let's pick this one. So I've got these two reactions, and I'm going to try and predict what the redox equation is going to be. So quickly tell me, who gains electrons, who loses electrons?
MnO4 would gain electron and Fe3 plus will lose electrons.
So that's going in the forward direction. This is going in the
Reverse direction.
So that's pretty much it. That's higher one. And this over here is the lower potential. And then we can make the overall reaction, right? We can just sum up the reactants. But before that, we need to make the number of electrons gained and lost equal. So who do I multiply with what number?
You multiply the Fe3 plus reaction with 5.
So we're going to multiply that by 5, so that the number of electrons, and remember, this is just for balancing. It's not going to affect the E naught cell or anything. It's just for balancing equations. So we're going to multiply it by 5, and we're going to add up the reactants. The reactants over here are, this is the reactant, and over here, this is the reactant, right? So you add up the reactant, so it's going to be MnO4 minus 1. And 8H plus 1. No need to write the number of electrons, because they're going to get cancelled out anyways. So 5 Fe, 2 plus, and then on the other side I'll have my, also tell me what the E naught, the other side I'll have my products, which are in the first one, it's Mn, 2 plus 4H2O, plus 5 Fe3 plus, right? So plus 5 Fe3 plus. And what's the E naught cell for this?
0.75.
0.75. So 1.52 higher minus the lower one. So it's 0.75, which is quite a positive potential. So it's a very, very feasible. It's a very, very feasible reaction. So that's about it. Is that clear? This one.
Yes.
So then the next thing is, so remember this part is pretty easy. Like if you, I mean, all you have to do is just open the data booklet, which from now on, I mean, this whatever you need would be quoted with the question. So if I have, I mean, just focus on this. If I have iodine and I've got potassium, like these two. So who's going to gain electrons? Who's going to lose electrons? If I
Iodine
react,
is going to gain electrons and potassium will lose electrons.
right? So that's about it. That's pretty easy, right? Is that clear? I said, now the thing is that reactions are not exactly that straightforward, because they don't give you exactly what electrode to use. Like things, life would be very simple if they just told you exactly, like, I mean, you're reacting this with this, right? But that is not how reactions work. For example, so this is how an actual, I mean, you're going to do the same thing, but it's not going to be that simple. This is how it's going to work. I mean, sometimes they'll just give you a direct question like that, like the ones that we just did. But most of the time, when you're predicting a reaction, they'll give you something like this, like there's copper plus FeCl3, right? And they're asking you to figure out what the products are. Okay, that's, now they didn't tell you what the electrode is, right? I mean, they just told us that there's copper and nothing else. That's it. I mean, so I don't know what electrode to use. Like if I go over here, I'll have, if I look over here, I'll have, I mean, there's this copper electrode, there's another copper electrode, there's probably copper somewhere else as well, over here as well. So I'm not really sure what's going to happen to copper. Ranji, is this clear? That in this case, 1 second, hold on. Sorry. Hello, can you hear me? So do you get the point that we can't really figure out what the electrode is? Is that clear? And the same, so these are the steps how you're going to do that. First thing is, step number 1 is you write down your reactants. What are your reactants? And remember, ionic compounds, you have to be very specific about the ions that you have, because remember, there's not going to be any electrode for FeCl3. What you're going to have is an electrode for Fe3 plus and Cl. I mean, you're going to treat ionic compounds as two separate species. Like if you have NaCl, it's either going to be Na plus 1, something happening to Na plus 1, or Cl minus 1. So think of it in terms of ions. So if I write down my reactants, I've got copper, and I've got Fe3 plus, and I've got Cl minus 1, right? Raji, is this clear?
Yes.
So just remember, there's no such thing as FeCl3. You won't find an electrode for that. You either Fe3 plus is going to gain or lose electrons, or Cl minus 1 is going to gain or lose electrons. The second part is you write down all possible electrode reactions, whether they are gaining electrons or losing electrons. So now in your case, you don't have to actually write them down because the data would be there for you. You can just do all the working on the data. So write down all electrode reactions. And those reactions involve your reactants only. So they should, I mean, like you've got copper, you've got Fe3 plus, you've got Cl minus 1. So I'm going to write down all possible copper reactions. So over here, I'm just going to copy this over here. Whether it's gaining, whether it's on the right side or on the left side, doesn't really matter. Like if it's on the left side, conventionally speaking, in the forward direction, they're gaining. In the backward direction, they're losing. At the moment, I don't know what they're doing. I don't know who's gaining, who's losing.
Yeah.
So I haven't figured that out. So I'm going to write down these two reactions that involve copper because I had copper with me. So I'm just going to copy the copper reaction. What's over it went? 1 second. Okay. So I've written down the copper reactions, and now there's another reaction involving copper. This one, if you can see on your screen. I'm not going to select that. The reason is that in that reaction, copper needs NH3. Copper is reacting with NH3 to form something else, right? So in my reactants, I don't have NH3. There's no NH3 over here. Is that clear? Yes or no? Is this clear?
Yes, it's clear.
So remember, you're going to select those reactions that involve your reactants only. Then this one, I've got Fe3 plus. So I'm going to try and figure out all reactions involving Fe3 plus. So there are two of them. And I'm going to copy those two Fe3 plus reactions. There's no Fe3 plus anywhere else. So I'm going to copy those. So I've copied those reactions, and who else? I've got Cl minus 1 as well. So I've got two reactions, Fe3 plus with Fe, Fe3 plus with Fe2 plus. So, and then I've got Cl minus 1. Cl minus 1 is in C. So Cl minus 1 has this reaction. It also has this reaction, but this one over here is with OH minus 1. I don't have OH minus 1. So in this case, Cl minus 1 is reacting with OH minus 1 to form something else. So I'm not going to pick that one. I'm just going to pick the Cl minus 1, which is 1.36 volts. So is this clear?
Yes.
Just a second. So I've picked my reactions, and I've ignored those reactions that did not involve my reactants. Now the next part is easy. The higher potential. I mean, we just figured that out. The higher potential. The one that has the highest E naught gains electrons, or has the greatest, and the one that has the lowest E naught, what does it do? It loses electrons, right? And you need to make sure, one thing that you need to make sure is, make sure that it's your reactants that are gaining or losing electrons. I mean, it wouldn't make sense if, I mean, it has to be someone out of these three. Is that clear?
Yes.
So it's either going to be copper or Fe3 plus or Cl minus. Someone out of the three is losing electrons and someone out of the three is gaining electrons. So you need to ensure that it's your reactants that are gaining or losing electrons. I've put my reactants right at the top. So which one is the highest potential at the moment?
Fe3 plus.
Now you look again, which one is the highest potential?
Oh, Cl2.
So that's this one, right?
Yes.
But should I select that? I mean, this is fine. This is the highest potential, which means that this has the highest tendency to actually gain electrons. So who's going to gain electrons? It's Cl2 that's going to gain electrons to form Cl minus 1. Do I have Cl2 over here? I don't have Cl2. Is that clear?
Yes.
So basically, I'm not going to select this equation. Actually, I'm just going to totally ignore it, because it's not going to work for me. Now, excluding that, now which one is your highest potential? It's this one, right?
Yes.
And it works perfectly with our reactants. Like it has Fe3 plus in it. We do have Fe3 plus. So I figured out that out of the three, it's Fe3 plus. That's the one that has the greatest tendency to actually gain electrons. Is this clear?
Yes.
So I figured out one of the equations, and then I'm going to figure out the one who loses electrons. So who's going to lose electrons? Which one is the lowest potential?
Cu2 plus.
I mean, the Fe one has an even lower potential. I mean, this
Yes. Oh, okay.
but will we use this equation?
No.
We're not, because because I don't have Fe. I mean, I have Fe ions like over here. I've got Fe3 plus, but I don't have Fe, so this doesn't apply to it. Now the other one is copper. This one, right? Is that clear?
Yeah. Yes.
And we do have copper with us. So this makes perfect sense. So I've figured out who gains electrons and who loses electrons, and I'm just going to focus on those two equations now. So let me just highlight those two equations. So one of them is this one, and the other one is this one. Is that clear?
Yes, sir.
And I can just add up the reactants. I need to multiply the Fe3 plus equation by 2, I think. Right? So that needs to be multiplied by 2, and it's going to be what? 2 Fe3 plus. And in the first one, the reactant is copper, and the products are going to be, so the products are going to be in this, it's 2 Fe2 plus, and it's copper 2 plus. I mean, this was my reactant over here, and this was the reactant over here, and this is the product over here, this is the product over there. So that's my overall reaction, and I've found my overall reaction. I can figure out the E0 cell. Just it's going to be 0.77 minus 0.34, right? Is this clear?
Yes.
So now try doing a similar reaction. So now try doing a similar reaction with I mean, here's an easy one. I mean, you can already predict. You can send a snapshot, right, on WhatsApp.
Yes.
So
Yes.
try doing this one, Cl2 plus KBr aqueous.
Delta plus KBR. Okay.
So remember, Cl2 is a gas. I mean, Cl2 doesn't have ions, but KBr is K plus 1 and Br minus 1. So just like what we did over here. I mean, I'm going to share the board link as well. Where's the chart? Just a second. So try and do this one. And remember, you have the data booklet, right? Also remember that sometimes the ions can be tricky. So make sure that if you're confused about the ions, this thing over here has a lot of ions. Like if they wrote NaClO, I mean, for example, if they wrote NaClO, and you don't know what NaClO is or what are the ions in NaClO, you can immediately check that Na is +1. So you can see over here that there are separate equations for ClO -1. So all the ions are kind of listed in the data booklet. The same goes for, I mean, some of the ions could be like really, I mean, like VO2 plus, right? So you can have a look at the data booklet and figure out what is the formula of the ions. So try and do this one. I'll wait for the answer. And I'm going to give you another one.
Sir,
Yes, are you done?
I don't know which two equations to select out of the three.
For Cl2?
Yes,
Just a second. Let me just quickly write this. So you've got three equations, right?
yes, three. One for with Cl2, K plus, and Br2.
Basically, there's just three. Just one second. Let me quickly write them down. So you got a Cl2 plus 2 electrons, 2 Cl minus 1 equation, right?
Yes,
And that's 1.36 volts. And for K plus 1, you also have just one equation, which is plus 1 electron at equilibrium with potassium, and it's minus what, 2.92 volts.
yes,
And then you have Br2, and it's in equilibrium with 2 Br minus 1, and that's 1 point, what is it, 1 point,
0.07.
so that's 1.07 volts. So which one is the highest potential?
Cl2.
So there's nothing wrong with that. It's, you do have Cl2, right, as your reactant. Is that,
Then K plus and Br2.
so now so that one is the high, so you're done with who's going to gain electrons, right? There's
Yes.
nothing. So who's going to lose electrons? Who's the lowest potential? It's K,
K
right?
plus.
So that's going to lose
Yes.
electrons, but do you have K with you in your reactants?
KBr. So
No, you have K plus 1 ions. I mean, in KBr you have K plus 1 and Br is minus 1. You don't have K. I mean, if you have this thing, you don't have K, because K is the one
okay.
that's going to lose electrons, right? So you
Yes.
can't use this equation, because although this is the lowest potential, but then it's potassium that loses electrons. You don't have potassium. You have potassium ions, you don't have potassium. So the lowest now is the Br minus 1 equation, right? And
Yes, you do have Br negative.
you do have Br negative, so that makes sense. So those are your two equations. Is this clear?
Yes.
So try doing the same thing with, I'm going to give you, so try and do the same thing with this one is slightly, if let's say FeCl2 plus KMnO4. I mean, this one is going to have, I mean, remember, it's the reactants are going to be K plus 1, I minus 1. And over here, it's K plus, like over here, you have S2O8. So if you don't know what S2O8 is, I mean, you should either be able to predict what is the charge on S2O8. Can you predict that? Like, you know that potassium is plus 1.
2 plus 2 plus 2.
No, minus 2. Like, this one is plus, so this one would be
Oh, yeah, minus 2.
minus 2. And even if you don't know that, you can just have a look at the data booklet over here. So there must be, I mean, this over here, I think. There's S2O8 to minus 2 over here. Is this clear?
Yes.
So you can have a look at that one. Now, so basically, again, you've got three things over here. You've got K plus 1 ions, and you've got I minus 1, and you've got S2O8 minus 2. So you have to figure out who gains electrons, who loses electrons. This one is slightly harder because it's got more ions. You've got Fe2 plus, Cl minus 1, K plus 1, MnO4 minus 1. Plus, this is acidified. A lot of times, they'll write acidified. Acidified just means that if there is an H plus 1 involved in the equation, for example, MnO4, look at the MnO4 minus 1 equation somewhere over here. You'll see that every time you have MnO4 minus 1, there's H plus 1 next to it, right? So when they say acidified, it's not a reaction with the acid. So you don't have to worry about H plus 1. It's just that the equation will have H plus 1 in it. So you're going to pick those equations. Like if there was no H plus 1, then you would not be able to use the MnO4 minus 1 equations involving H plus 1. Is that clear?
Yes.
So try and do this one and the third one as well. Okay, that's your homework. Just try and make an attempt and send whatever you come up with. ठीक है
Okay,
Zach?
sir.
चले. Okay, let's continue tomorrow then.
Tomorrow, what time?
7. It's just that
Okay.
weekend it's I mean I'm not really sure where I am at. So I mean tomorrow is 7, that's fine. Weekdays is 7. Okay, take care. Bye.